Okay, so hi, my name is Jakub Beránek, and I would like to welcome you all at the second Rust Prague Meetup. I'm very happy that there is so many of you. We didn't expect that because the last time we had the first run of this meetup, it was like 20 people, and we couldn't fit inside the room anyway, but now we have much better venue. So maybe you have noticed that this meetup will be actually in English because I think that it's better. In Prague, there is a lot of people that might not speak Czech, so this should be more like inclusive for all people that they can understand, hopefully. And we also have, like, I would say, international speakers today. So I think this is a more compatible way how to do it. So at the beginning, I would like to thank Pavel, who basically organized this whole event and also the last one, and also Martin, who has helped us find this beautiful venue that was actually provided by the Department of Distributed and Dependable Systems. And I think that this is quite fitting because Rust is a really good tool to write both distributed systems and dependable systems, and it's even better at writing distributed systems that are also dependable. So I think that is a very cool thing that we are being supported by this department. So I have just a very few slides about like the history of these meetups, just to get some kind of overview. So actually, there were already some meetups in Prague under this Rust Prague Meetup group. It was, I think, in 2017, there were like 5 meetups. And then maybe there were some other meetups in 2019 that Pavel was also organizing. Is there actually someone here that attended one of these meetups like 7 years ago? Okay, cool. Yeah, so this was, it seems that there was some traction for Rust in Prague 7 years ago, but apparently it was kind of discontinued, and then I don't actually know what was happening because I didn't find any history on that. But okay, but COVID was 2020, so there is a little bit of a gap there, but okay. There are actually some meetups happening in Brno, so there is something that is called Rust Beer, which has been happening more or less every month, I think last year, then it stopped in summer, and now it has been resumed. So if someone has a way to Brno, you can attend it. There are also some regular meetups in Bratislava. So it is organized, I'm not sure if it's organized by some company or if it's a community meetup. I wasn't in Bratislava yet. Was someone at the Bratislava meetup? Okay, it's too far, anyway. So they have some meetups also in Slovakia. And I'm actually trying to bootstrap some meetups also in Ostrava. So next month, on the 17th of April, there will be, I would say, the first Rust meetup in Ostrava, organized by the Tech Meetup group. So if anyone thinks that it's fine to go these like 300 kilometers to the east, you can visit our Ostrava meetup. And regarding this Rust meetup, we had a first one in January. This is a photo of some kind of like after party from the meetup. So yeah, we had actually just one talk because the second speaker didn't arrive. If you want to take a look at the recording, we actually had a live stream on YouTube. So if you can check it out, if you want, you can check it out what we talked about. I had a talk about the governance of Rust. But actually, we are like starting, right? Like this is the second meetup. So it's not like we have everything prepared and we know everything. We are trying to find out what should be in those meetups. Like what is the content that people interested in Rust are actually wanting to hear about, right? We don't know yet. So this will be like a half and half. Like we will have 2 talks, but we will also have some kind of discussion about various topics. We'll see what will happen. So we'll be also glad if you could let us know, like, what are the topics that you are interested in. Do you want to know, like, I don't know, some internal details about the compiler or the standard library or some these deep technical topics? Or do you want to know about how is Rust being used in companies? Or do you want to know what is it like to teach Rust at university. So we have a lot of experience, I think, amongst all of us, but we don't know what they want to hear about. So there are some online communities. I will show them, for example, on Meetup or Discord. So if you have some topic that you would like to hear about, you can just put it there, and we can try to prepare a talk about it. Okay? Yeah. So this was our first meetup in January, and then basically at the same time, the Brains company, which is also using Rust a lot, has kind of built their own meetups, and they had one in February. And right now, the plan is that this Rust meetup will be like every 2 months, and it will be more or less interleaved with the Brains meetup. So it seems that there will actually be like one Rust meetup in Prague every month, one from Brains and one from this Rust Prague meetup community. Okay, so last year I thought that there is like nothing with Rust happening in the Czech Republic. Now we have the 2 meetups in Prague, one in Brno, maybe one in Ostrava. So yeah, it looks like it's starting to build up. Okay, and one thing that I would like to mention is that actually a lot of people have been asking me and Pavel and others about like what is going on with Rust in the Czech Republic. Like what are all the interesting events and communities and meetups and so on. So I was kind of annoyed that I have to answer all these questions all over again. So I built a website which is accessible at rustlang.cz. And on this website, you can actually find like an index of all the Rust stuff that is happening in the Czech Republic. So we can actually take a look at it. Yeah, so it's just a very simple website that shows like what are the online communities, meetup groups, Discord, what are the events, some recordings of talks, some education. So if you want to see like where is Rust being taught at universities, you can check that out, or some trainings, or some companies that are using Rust or are searching for Rust developers. And it has a RSS feed, so if you want to subscribe, you can put this into your RSS reader, and you will know about all the news about Rust. Well, not all the news, but all the news that will be on this website. I'm trying to gather like everything that I can find and put it here. Okay. So yeah, so this is like the index of the Rust stuff that is happening in Czech Republic. And yeah, and basically to conclude, I would just like to mention 2 things or 2 news from the Rust project itself. So I don't know if you have saw it online, but the Rust is actually participating in the Google Summer of Code project this year. Is there someone who ever heard of Google Summer of Code? Okay, nice, a lot of people. So it's basically a program by Google where they want to match students and people that are like beginners in open source with companies that have open source software and then that are looking for new contributors. So basically the company says, I have some project, I want to find someone who will work on it, and then Google matches the students or the beginners in open source with the companies. And if they find a good match, Google will actually pay these people to work on the open source over the course of 3 months, so that's the summer. And you will also get like a very nice record on your CV that you had participated in Google Summer of Code. So if you would like to check out this program, maybe you're a student, maybe you're someone who is a beginner in open source, you can still try to participate this year. So until the 2nd of April, you can send project proposals, and we will then evaluate them and select the best proposals that we want to move forward. So on this URL, you should find the list of project ideas and topics that the Rust project wants to work on. And if you find something interesting, you can come, for example, to the Rust Tulip, which is our discussion platform. And you can ask around and see if there is something interesting. Actually, you can also go there if you don't want to participate in Google Summer of Code. Like on the previous link, you can, if you just Google Rust, Google Summer of Code, you will find a repository that has like 15 or 16 projects. And if you'd like to contribute to Rust, you can just take a look at the project and start working on it. It doesn't even have to be with the cooperation with Google. So if you, for example, like me, a few years ago, always wanted to contribute to the project itself, like to the compiler or the infrastructure, the standard library, but you didn't know where to begin, on those links you can find the places where to begin, right? Like some ideas what you could work on with mentors that can help you and some guidance on what to do. Okay, and that's pretty much all I wanted to say. So now we will begin with the first talk, and it will be from Martin Kolařík from Edhouse, and he will introduce himself because I think that is actually better. So let us just swap the microphone. Can you hear me now? No? Yes? Okay. So it should be okay. Thank you. So something about me. I'm Martin Kolařík. I'm from Edhouse company. Here's the logo of the company. I'm working as an engineer manager for 40 people, and the company Edhouse is creating software for companies who work in the field of science or technology. For example, my responsibility is to work with customer Thermo Fisher in the field of electron microscopes. So we are creating softwares for the tools Thermo Fisher sells to Thermo Fisher's client. I started with Rust 4 years ago, and I completely fall into love with Rust, so that's also why I am today will tell you something about WebAssembly and what it means for Rust. My first question, how many of you, maybe of us, ever created web application, some front end in any platform, React or also? And how many of us used Rust? Perfect. And WebAssembly and Rust? That's nice. I was asked to, of course, I invited myself to this meeting, so thanks. Where is Pavel? Thanks to Pavel. And what I will tell you is something about WebAssembly and Rust from the top level as an overview. So if anybody here uses Rust already and WebAssembly, it will be something like a repetitory or so. So I will talk about WebAssembly in 3 blocks. This. And let's jump directly to the first one. So what is WebAssembly? WebAssembly is first W3C's open standard. So this is something what is managed by this consortium. It's a binary instruction format, intermediate language, and because it's intermediate, it's implicitly portable. It's also stack-based low-level virtual machine which takes this intermediate language and compiles this language into native language for any sort of processor. And WebAssembly, when it was created, it was approximately 1915, I think. Primary goal was to enable high-performance applications on web. So the purpose was to get browser, and in browser, the first language to use is JavaScript. Interface is available for JavaScript, and JavaScript is a bit slow sometimes,
So they wanted to have a mean how to run applications which are performant. How WebAssembly works in the browser? First, because it is binary format, it need when the file is loaded, it doesn't need any parsing, so it simply loads faster. Today, it's supported in the majority of web browsers, including mobile platforms. Technically, WebAssembly file or WebAssembly which runs inside the browser is a module, and it's encapsulated, and as a module, you must specify exports and imports to communicate with different modules. Different modules, it can be JavaScript, also different WebAssembly module. And because browser API is JavaScript, as I said, everything what is communicated from WebAssembly and to WebAssembly must be marshaled. So marshalling is needed. It can be for primitive types very straightforward, and it's complex, of course, for more complex types like objects or so. But it's by definition, because WebAssembly is integrated into browsers, but not so deeply. JavaScript still is the first language to use. WebAssembly outside the browser, it happened that when independent intermediate language was created, this language started to be used everywhere. So today, you can find WebAssembly in embedded engines, typically in games. There are plenty of runtime environments which can run WebAssembly files, and because the nature runtime environments is something for anything you can run inside this environment, so the purpose is general. For instance, Vesmer, Wassentime, and VAMR, so VAMR WebAssembly micro runtime. It has about 100 kilobytes of code, I think. So it's tiny. WebAssembly can run inside this runtime environments completely standalone. WebAssembly is used in clouds. And what is important outside the browser, there is system interface defined for WebAssembly system interface. What is something like definition of operating systems API available inside WebAssembly runtimes to access resources of the host computer where the environment runs. So you can create nowadays WebAssembly portable binary, which you can put into many environments, and if the environment supports WebAssembly system interface, you simply get your program running in plenty of places. So that's linked system interface and the fact that WebAssembly is portable binary format. The last thing about WebAssembly, I found this quote. It's very nice. So there is a question, maybe. Is it better? Okay. I think this is This is truth, and what is important from my perspective is that having runtime, for example in cloud, it's exactly what typically Docker does. So you have something prepared, so something what do you want to run, and from this point of view, WebAssembly system interface and WebAssembly runtimes are competitors to Docker. So WebAssembly and Rust. First, I must apologize for a small mistake. I said, Pavel, that it's first tier platform, but this is not true. WebAssembly in Rust ecosystem is put to the tier 2. What this means? It means that platforms for WebAssembly are guaranteed to build. So each night when completely standard library and Rust compiler is built everything what is needed for WebAssembly. It also means that for WebAssembly you can use complete standard library of Rust. And currently there are two main targets you can use for compiling your program. WebAssembly 32 Anown, which is used for front ends and, for example, for Node.js or anything what can run browsers WebAssemblies. And the second is WebAssembly 32 WebAssembly system interface P1. And this is ready for WebAssembly system interfaces runtimes. You can easily install this target by Rustup target at what you want, and then you can immediately build, after loading and installing the target, immediately build your program as you know using Cargo. WebAssembly and ecosystem, I said that complete standard library is available to be used in WebAssembly, but standard assembly is not enough. Currently, all principal crates I know are ready to be used in WebAssembly, so cd chrono lock. There are also crates with executors for running asynchronous Rust in WebAssembly in browser as well. So Tokyo with some async std wasn't binning and futures, and also many others, ciphering, caches, generating, reading, PDF, XLSX, image processing, and so the ecosystem is very rich, and you can, if you want, of course, you can put complex tasks, complex computations to the browser using WebAssembly and using Rust today. Okay, so when you need to build something, when you have some program, simply when you install the target, Rust compiler is enough to prepare WebAssembly. So when you compile your program for the target for WASI, it runs. And also for front end, Rust compiler is enough in principle, but usually there's something more, because of marshalling. I have somewhere in the previous slide. It is better to create boilerplate code and glues by some tool. So usually when you are creating program for browser, you are using tools which take the created, built WebAssembly and post-process the WebAssembly sometimes. So you can use bundlers, optimizers, or anything what you need in the term of post-processing, like strip some sections of the WebAssembly, debug symbols, text symbols, or so. I mentioned Webassembly, rollup. These are bundlers used in general for any web applications in JavaScript world normally. And also Webassembly, which is a single tool from the package Binarian. Binarian is package created in the C++ world. And because WebAssembly is universal and shared between Rust and C++, you can easily use this tool. Why I'm talking about Webassembly? Because it's a very nice tool to shrink down the size of WebAssembly. Very nice tool to manipulate the WebAssembly, so it is used usually at the final stage of building the application for the web. Okay, so what about Rust, WebAssembly, and front end? As I said, Rust needs to communicate with JavaScript world from inside the WebAssembly module. What is possible immediately are primitive types. What is possible with some tooling, you of course can write anything you want yourself by hand. But there's a great Webassembly which can create exports and imports and in general glues between WebAssembly and JavaScript, and also Webassembly have support to easily access document object model, which is the web page, you know. And very important point, second point on the slide is create websys. What is technically generator, and from user perspective is an interface to all browsers API. Browsers API are many. Specification for these APIs is again maintained by W3C. The format used is WebIDL, Web Interface Definition Language. And the websys takes these definition files and creates pure safe Rust API for the browser. So this is ready, this is prepared for you. It's sufficient, it's enough to reference websys as a crate in your cargo TOML file. And you can access anything what browser can run from the WebAssembly and from the Rust. Rust and front end. As you would expect, there are different levels of creating a front end application. And Rust is not exception compared in comparison with different environments. So if you use websys create directly, it is the same as you write your application in plain JavaScript inside the browser. So no tools, no libraries, nothing more. There are crates. I mentioned you and Dioxus. This is something like React. From the philosophy point of view and also from the level. So both crates, both frameworks are preparing for you rich environment how to do things. And you can use them if you agree with this way, this philosophy. Or, for example, create Leptos. And this is something like Sycamore or P-React signals. Different approach, different models. What is shared between these three environments or frameworks are signals. So if you want to create your front-end application, you simply can choose what you know from other worlds and start to write front ends in Rust. Okay, but back. Here, what I did, Lepsys, U, Leptos, I compared this framework with something what exists in the world and is used for creating front-end applications. But all 3 points, all 3 lines are driven by web world. So this is something like web is done. And Lepsys, U, Dioxys, Leptos follow the way and repeat the behavior and repeat the framework to use them in a very similar way. So if anybody knows how to create application in React, he can sit down and use U, and he will feel very pleasantly like he writes React also, of course, in Rust. But, and this is what I appended Rust for the second time to the caption of the slide. We are using Rust, and Rust has different ways and different possibilities how to express things. And this is something what, of course, I would recommend. And in Webassembly and front end, you can fully use what is used in Rust in any other field where Rust is used. You can use fully idiomatic Rust. You can use fully normal asynchronous approach, which is used in Rust. So you can use the Rust as the Rust is used. So that's the point. I have first line something for state handling, second line something for cooperation between states and view, FRP, functional reactive programming, the create future signals. I think it's one of the small gems in Rust ecosystem. So FRP system completely based on futures. And I added the next crate, dominator. It can be any other crate which can consume signals. So together, just for example. And here I'm writing what I'm said a minute before. So you can use Rust as Rust is expected to be used. You can use Rust when you are using it now, if you are using the Rust, of course. And you don't need to follow any existing way how web applications are done. That's something what is, from my point of view, important, because you can use the full power of Rust without closing himself or herself to some boxes of previous decades how web applications were done. So it's something like trade-off. If you know how web applications are built, yes, you can do it in Rust the way you know. But also you can create web applications using Rustway. And this is something what I think is the right way, of course. Rust is for backend and also for front end. All 4 points in this slide are simply advantages of having Rust on both sides, in backend and in front end, because you can reuse what you know when you programming in Rust in front end and in backend. It's the same. You can work with the same crates. Again, this is something about knowledge and about customs. There's no problem to use the same crates in browser and also in the backend. You can reuse your own business logic. So you can have parts of your algorithm in the backend and also in the front end. Also, you can have this code in one crate, in one source file, and use the source file in both ends. You can share types. This is something well known. For example, when you need to communicate somehow between front end and back end, and you are using gRPC or so, you typically must generate entities or glue code for backend and also for front end. Also, there are many different ways how to generate something for something, generate TypeScript files for some communication protocol or so. In Rust, you can use what you have defined in the backend directly in the front end. So don't repeat yourself. If you fix something in the code, you fix the bug in both places, in front end and back end. So when you use Rust in both back end and front end, you simply write everything once. That's perfect. Rust is versatile, so some repeating of known facts. So you can use Rust in cloud services for networking, distributed systems, for command line applications, generic tools, embedded systems, so in very tiny microprocessors, and in front ends. Desktop UI is something what is behind, but it's getting better, I think. In my experience, using Rust in front end is far the best solution. Just because I tried many ways, and I created many web applications. In plain JS, I tried jQuery 2 weeks or so, React, Preact, and so. Now I'm creating my hobby projects completely in Rust, front end and back end, and simply for me, this is the right way to do. Very likely, my experience is linked to these points, that simply I want to have things defined once at one place, and I want to share what I created in the application between these two worlds, client, front end, and back end. So I, again, recommend, please use Rust in front end. Okay, so let's try something. And I prepared a very minimal example, and I will show you the code. So, okay. Very small code. This is cargo TOML file, so there's nothing. What I prepared on this line, simple compilation of my crate with the selected target, Webassembly 32 ennoun. When I run this line, it compiles, of course. What my application does is very straightforward. Because I'm using a raw approach, no glue, I define some external function calling lock. I'm calling this lock from the main function of my application, and also I have created something what is exported from my module. This is everything. This is just for purpose to show how Webassembly created communicates inside the browser. I'm creating no nodes, no HTML, but I still need to have HTML page to load my application. So what is here? Here is some headers, and here is the important part. This is something what must exist in any web page which loads Webassembly. And this is something what is very well described. This is web browser API for using Webassembly. So I'm fetching Meetup Webassembly, instantiate this Webassembly. Then I'm calling the main function. Then I'm calling add function. Then I'm logging the result of the add function. And what I'm also doing is exporting from this module to my module lock number. I'm exporting from the HTML file function, which takes number and writes log message to the console of the browser. So that's all. The Rust source is very minimal. I compiled it. That's all. And how it works? It's very easy. I have small web server, of course, in my application, so I can serve Meetup HTML. When I show this HTML, you can see nothing because there's really nothing. But what happened inside development tools? You can see here. It is small, but this development tools and console is difficult to make it bigger. And that's it. So 42 is printed inside the main RS. And here is the lock, which is done by the HTML file. So main calls log number 42 is shown, and also the second part, Meetup HTML, once the Webassembly is loaded, console log is called with the result of adding 1 to 2, and what is displayed, 1 plus 2 is 3. So this is very minimal application which doesn't use any of processor, any bundler. You can create your application in this minimal way. Of course, this is usually not enough, and usually you need to transfer objects. So that's why bundlers or Webassembly is used, for example. Okay, and last thing I would like to show you is something bigger, and it will be just showcase something like, look at it, it works. And also in the code, I can show you and show you. First, I'm using Webassembly, but I'm using no bundler because I have something like bad experience from my JavaScript ages. So when I found that I'm able easily to create WebAssembly and then do something with WebAssembly, I created batch file for myself, and that's all. That's all deployment. So I built my project, and I do some stripping and creating glues by Webassembly, and if I want, I can optimize the build somehow, so strip debug symbols or so to get the resulting WebAssembly file minimal. And also, when you compare the main of my application and main of the previous minimal application, you can see that there is plenty of things. So some logging, initialize, some binding routing to the browser, some states and starting of the application. This is main only, and here I have many sources, and I usually divide parts of the application to states which are completely independent on view, of course. I'm using global static objects as states, and here it is normal Rust, you can see. So I'm using the basic idioms, I'm using the code as you would expect to code Rust, I think. And this is my part elaborating states, working with states. And on the view side, I'm using, I mentioned dominator crate, so I'm using the dominator crate as a base, but I have something above the crate, so I'm using primitives. I have my cascading styles inside my WebAssembly application, so I have no files except the WebAssembly. And also, as you would expect in web applications, there's something like boxes, classes, childs, and so, for example, dialogues modal. This is view created in Rust. This is normal Rust. It can be very complex from the point of view that application can be very complex. The Rust is still the same Rust as in backend, as in command line application, as in cloud also. How looks this application? Just a brief look at it. So this is my commercial but hobby application. So I have something for leading competition in dance sport. So this is UI which is created in WebAssembly in Rust in the way I showed you shortly. So I have dialogues, I have everything what I need. What is something special, and I needed it, and I think it's very nice because there are many operators during the competition. I needed the UI to have distributed, so everything is synchronized. When somebody changes something, it in a few milliseconds appear in all other clients. So this is something what is not so typical in front ends, because typically there's one user, one client, which does what he wants, and backend serves many clients. I need to synchronize clients over one single competition, and I like it. And I like it many things which I'm using directly from the Rust world, because it let me how to do things. This is something what I can say today, looking back, because of course when I started to work with Rust and in this application, I didn't know that Rust will lead me and that this happened. So this is something like retrospective, or some thinking about what happened. So for now, this is everything I wanted to tell you. So maybe minor discussion or questions. If you have bigger questions or so, I will be here to the end, and also I will attend pub. Will be there some.
We will find something.
Yes, we will find something. This is the response, so you can reach me and we can talk about things. So please, is there any question?
From what I recall, some of these functions are POSIX-like
Yes.
in nature. How do you deal with asynchronous access for operations that you don't want to block
Do you know the name Joshua Witz?
Yes, he's a colleague.
Yes, a colleague in Microsoft. And as far as I know, he's just working on extension of WASI, an extension which...
It wasn't that.
Yes, but he works on the interface itself, which should bring full support for threading and asynchronicity.
I'll ping him.
Okay. So thank you. If there are no questions, that's fine. So thank you. And I think we will meet in the future somewhere, sometimes. Thank you.
And now I think we'll take a short 5 minutes bio break, and then we'll continue with the second talk. Okay. 1, 2, 3. Can you hear me? Well, blah, blah, blah. Okay. No? Is it not? Can you hear me? No? Okay. So let's start with the second half. I would like to thank Martin for his talk. I think that especially the demo at the end was quite impressive, and that it really showed that the Rust is very versatile and it can be used pretty much anywhere. And now we'll have the second talk by Viktor Ciura, who is from Microsoft, but he's also from the C++ world. And I'm very glad that he came here to share his knowledge and experience. Okay, so take it away.
Thanks for inviting me. Hi, everyone. I'm Victor. I hope the sound level is okay. I can shout. Just tell me. I can be really loud if necessary. Also, I tend to be fast, and when I get all excited talking about stuff, I tend to go quickly. So at any point, feel free, like stop me, wave, shout at me, something. So the format I had in mind was sort of a short talk. I have a few slides for me. Number is pretty low. I usually have like longer format talks. So the idea is to encourage a dialogue. So I want sort of this to be a teaser, conversation starter. I'm going to present some ideas. I'm going to challenge some, let's say, common practices. I'm going to throw some bricks in some theories and tell you about some experiments that we've been working on. And hopefully you can share similar things. Ask questions, share your experiences, comment, challenge the things I'm saying. I very much would like this to be more of a conversation rather than me preaching something, because I don't claim I have universal truth to present. I have some theories, I have some data to back those theories, I have some assumptions, and I want input. So that's how I expect this to sort of roll out. Just as a as a framing, yes, I come from C++. I've programmed professionally C++ for over 20 years now. I sort of started hobby-like projects in Rust a few years ago, toyed with it, learned from it, tried to borrow some of these ideas, and sort of, I think it improved my C++ style in general, learning functional programming languages, learning from some of Rust idiomatic things. I was trying to sort of bring those to C++ as well, to various degrees of success. So about the end of, towards the end of last year, I made the actual transition, and I am actually paid to program in Rust now, which was a big change for me. So I worked on various projects. Some of these are here. For a while, I worked on the Visual C++ team at Microsoft, and I now moved to M365 Core, which is a platform, and it's relevant. I'm not advertising Microsoft. I don't think it needs it. They sell too many things already. But it's relevant for setting the context. So the context is that I moved to a team in M365. So this is an organization that powers the biggest cloud ever. And it's sort of I wouldn't say it's fair to say it's a competitor to Azure and AWS, but it's a specialized type of platform. So this is the platform that drives big data at Microsoft. And that includes, more recently, the AI workloads, which are pretty intensive, and huge amounts of data supporting products and services like Office and Outlook and Exchange and Teams and everything. So a lot of the heavy data intensive products and services at Microsoft are built on top of the M365 substrate platform. And we were tasked with building a set of foundational libraries in Rust to help build these microservices in Rust. These microservices are currently written either in C++ or in .NET, most of them in .NET nowadays. So my team is working on building foundational components from low-level things up to turnkey solutions and Lego-like things that you can cobble together and create complex services that are efficient. And I'm going to take you to the whole other opposite end of the spectrum. So in the first talk, we talked about front-end stuff and how you can bridge this with Rust and use the same language for front-end and back-end. And now I'm going to take you all the way down the other end of the spectrum, and then I'm going to focus exclusively on what happens in the data center, what happens in the machines that run these services, and this whole presentation is going to be all about performance. So some context. Servers nowadays are 100 to 100 cores machines. There's huge beasts with various NUMA regions. And the idea is you want to squeeze the most out of this bare metal, regardless if you're running directly on the bare metal or if you're running in some sort of containerized way. So you want to reduce latency, you want to reduce core utilization so you can squeeze more stuff in the same machine. And for many of these services I mentioned, data-intensive things and huge amounts of data. So I/O latency is a big thing, and in general, many of these things tend to be I/O bound rather than CPU bound, which is sort of expected for the nature of the workloads. So some of the goals is to define an application model for Rust processes in this context, in the context of these microservices. Of course, I mentioned high performance. You want to build a programming model that is simple to understand and program against, and ergonomic and intuitive, sort of correct by construction kind of thing. So all the sort of expected desirables. And the model is the thing that I'm going to lean towards, because this is an architecture talk. By the way, it's going to be like, I think I have maybe 1 or 2 slides with Rust code. Everything is architecture. But it heavily relates to Rust. So the model relies on cooperative multitasking as opposed to preemptive scheduling. The idea of building something with one OS thread pinned to each core and asynchronous operations produce tasks which are sort of enqueued in this single-threaded model. And we have, conceptually, we want to build a per-thread task queue to service each of these CPU cores. And benefits of such a model, nothing is perfect. Again, benefits are faster serial performance, non-linear scaling, reducing tail latency for these I/O-heavy operations. This is the biggest thing that we struggle with. But there's problems, like this model doesn't fit well with compute-intensive tasks, and when you have some very heavy, CPU-heavy operation, it can introduce delays in I/O processing if it hogs a particular execution thread. So, and of course, you have typical starvation issues when you have these many core machines. So I'm going to try to set a frame here, and I have some visualizations to help with this, sort of build this mental model. Maybe for some people, the visualization helps, rather than me waving my hands. So I'm going to try to contrast compute-heavy workloads with I/O-heavy workloads to see why solutions that fit a particular workload don't work on the other as well. So for CPU compute heavy workloads, a single task takes sustained batch of compute. So it will keep busier a particular core. So if we add more cores, we can obviously split this work if it's possible, but in general, you can always find a natural way to split this work. And by adding extra cores, you cut the task processing time dramatically when you split it many, many ways. But this doesn't come for free. You pay some synchronization cost. So you end up having some checkpoints, some points in the computation where you need to sync, or you have these bottlenecks between these otherwise parallelizable execution streams. So there's things where you need to access shared memory, you need to sort of write back some results or intermediate results and so on. Or you have, even worse, you have dependent operations that are not properly sequenced. So you gain a lot by this spread out on multiple cores, but you pay with some overhead for this synchronization where needed. So now for IO-heavy workloads, you end up having lots of these little bursts of computation. So most of the times, a processor will just wait for stuff to become ready. Either read something from the disk or wait for something from the network. Most of the time, reading from the network card is what causes these stalls. So you end up having like lots and lots of these bursts of computation where the CPU needs to jump in and do something, and then it needs to suspend and say, okay, I have nothing else to do, I need more data. So you have like lots of these things rather than continuous spans of CPU-intensive computation. So what we do in this programming model is you generally tend to fill the gaps. So what you're trying is to interleave these spurts of computation. You try to squeeze into these gaps on the same thread, multiple of them, so that when the CPU waits from some I/O to come from the network card or from disk or whatever, it does something else in the meantime, so it doesn't stay idle. So when you spread this over multiple cores, you end up having more waste for these types of workloads. So the overhead is a higher fraction of the total task of computation. So both throughput is lower and tail latency is tends to be higher when you're doing this kind of model, when you're trying to spread out across multiple cores, and they each have to somehow synchronize and schedule, interleave these micro tasks on their execution threads. So it works, but it increases tail latency, and that's not a property that you want from a responsive service, right? So what you want to do is build an isolation layer. So the programming model that we're examining and we're testing and we're constructing is an isolation model, where we try to insulate these execution threads and pin them to particular CPUs and build sort of a almost single-threaded model in each of its bubble in sort of way. I'm going to show more details about that. So we're trying to give them independent tasks to accomplish and avoid sharing any kind of memory between these execution threads. So this is where the shared nothing thing from the title comes from. Pavel was asking me, what the hell was that talk about? Like, what do you mean by shared nothing? So shared nothing fits surprisingly well with the Rust programming model. Because Rust in general tends to be a lot stack heavy in how it favors allocations and how you have deterministic destruction and how it lays out structures in memory. the way you have the programming model to be very explicit about when you're doing any copying or cloning, again, is a model that lends itself very well for this kind of isolation model that we want to build. Trait bounds like send and sync and negative trait bounds help you model these concepts and get type system guarantees about the things that you're trying to build. So rather than having conventions and sort of documentation about how these APIs are supposed to be used and composed together, you want to lean heavily on the type system to ensure that APIs and types are used in the right way and things access memory in the way you want. And by the way you want is what the next slide is about. So a bit about NUMA architecture. How many of you have heard about NUMA architecture before? Okay, I would say less than a third of the room. So don't worry, I came prepared. So traditional computer architecture is you have your CPU, which is the thing on the left, and you have the RAM, which is the thing on the right. Yes, that's a RAM. And you need to read stuff from memory and do something with it, right? And if you want to add more CPUs to the thing, they all need to read from memory, and there's caches, various levels of caches in CPUs to help with that, to reduce some of these latencies, because going to the RAM is much slower than reading from the cache and so on. So you have all these sort of levels of indirections, each with a different kind of latency expectation, right? So what happens when you throw a lot of these CPUs? So your traditional consumer-like machines will have, I don't know, 8, 16, 32 CPUs. But in data centers, you end up having huge machines with over 100 cores. And their architecture tends to be very different from what you see in traditional consumer products. So if you throw more CPUs at the thing, so how do you end up? Sorry, question? No. So how do you end up scaling this thing? How do they all end up querying the memory, reading from this shared resource? Because they all do their own business, and they all have their own caches, and they might even share some levels of the cache. But they do their best, but at the end they have to hit the main memory at some point, right? Those caches need to be loaded from somewhere, right? So this is where non-uniform memory architectures come in, where when they offer you more cores, they also segment how you access memory. So they tend to pool memory in different regions. You might have these NUMA nodes even split up in different packages on these fancy boards with multiple packages. And by packages, I mean the actual thing you plug in the socket. And they provide sort of some memory boundaries. So it's sort of like memory islands, where you partition the address space of the process, but it's actually in physical different memory banks, which end up being, some of them end up being closer to some cores, and some of them end up being farther away from some cores. So you will no longer have predictable latency for accessing the RAM. You will have fast RAM access, and you will have slower RAM access, depending on which parts of the memory you're reading from, right? And from which CPU you're doing that. Then I try to sort of draw here something like, the contrast sucks. Sorry about that. So I try to model the idea of memory distance. And by that I mean if a particular core reads from memory that is in its NUMA node, then it's a short distance, and it will be a faster access time, lower latency. If that core ends up reading memory from a memory bank that is in another NUMA node, you can do that. So the memory, when I say isolation barriers, that doesn't mean you're not allowed to read that memory. You're allowed to read it, but it will be slower. So you have more latency accessing memory that is not in your NUMA node, right? So, software that is written without thinking about these architecture designs and about these NUMA architectures, they tend to suffer from what they call NUMA effects, right? So they tend to not scale well. And particularly software that ends up reading all over the memory or doing a lot of synchronization. Things like when you end up sharing a lot of things, a lot of data structures that are protected with some sort of exclusive lock, but they're all sharing. So they're all like multiple computation, multiple threads end up going to a single location to read. That location might be closer to a particular thread, to a particular core, if you're setting any sort of affinity for that thread, but might be really slow for another one, right? And even if you're not using any kind of, let's say we're talking about an immutable data structure. Let's say we have a read-only data structure. So we say, oh, it's a read-only data structure, I'm only reading it, then I don't need any synchronization at all, right? All threads are just reading it. That's perfectly fine. It's defined behavior, right? But even then, some threads are going to suffer because they're going to be farther away from that data structure. Because that data structure is on a particular memory region, is in a particular NUMA node. So if you're lucky and you're reading that data structure from closer, it's going to be faster. If you're reading it from farther away, it's going to be slower. I think I beat this point enough. And the idea is that you don't really control that. So if you have knowledge about the architecture of the system you're running on, and if you're pinning the threads, and if you know what you're accessing, then you have predictable response times for these reads and writes. If you're not programming with this in mind, it's going to be unpredictable, right? It's going to be slow or fast depending on how you're lucky and how your scheduler does things. And this is where a traditional thread pool or a traditional work stealing system is not appropriate for these systems, for these architectures, because they will just try to organize tasks into this, let's say, a thread pool, right? And this thread pool is going to manage the hardware resources and allocation and see, okay, I'm going to place this task on this execution thread. Oh, I see this execution thread is starving. I'm going to steal some task from this queue and move it to this execution thread because it's idle, so it can pick up more. So it does all the CPU load balancing. So it balances well for spinning up CPU and avoiding having it idle, right? So it revs it up and it tries to do uniform utilization of all cores, but it does that at the cost of thrashing memory. It does that without having any considerations for these layered memory architectures, right? So you end up having lots of cache thrashing because of the frequent context switches that you have, because usually when you do these things, you end up having to use actual OS threads at some point, and if they context switch a lot, they will thrash the cache. You'll have really bad memory diffusion problems because you're mixing in even if you're having a good fragmentation factor for the memory. So even if you say, okay, I have a good allocator and I have a pretty compact layout for my data structures in memory, if you end up diffusing components in memory that are unrelated functionally, then you have a low fragmentation for your memory, but you have lots of diffusion, and then you end up loading in cache things that are unrelated, right? So these kinds of execution runtimes that do thread pools, that do work stealing things, that try to maximize CPU saturation, they usually are very poor performing in terms of how they access memory, right? And these have effects on latency, right? So what you want is to build a programming model that is aware of these things, and it tries to reduce some of these NUMA effects when you scale up, when you go to 100, 120, 200 cores and so on, right? So you want to scale and not get any degradation from these things. And this is where you need to lean on immutable state, on memory isolation, and have very precise synchronization points and very deliberate things. And I'm going to offer some mechanisms for this. So let's say this is my first Rust code on the slide. And as you can see, I suck at it. So let's say I have some kind of large data that I get into a function, and I need to do something with it, right? So the idea is on which thread will this do work function be called, right? And access this large data structure that I need to work on, right? So if this data lives on a different NUMA node, then, and we have to call this function repeatedly, we're going to pay the cost. I think I explained why. But let's imagine, and this is where the make closer function does a lot of magic, and in this case, nothing. But let's imagine this make closer function is much smarter than a simple clone, right? This is as much as I could do without an NDA, right? So, but let's let our imagination go and think about what this make closer function would do, right? So this make closer function would say, hey, when you're accessing this piece of memory, right? And again, leaning on the type system to be very deliberate how we get these handles, these references into memory, right? When you're accessing it, if I can tell that this memory is not collocated on the same NUMA node as this thread that executes this function now, I might choose to do a clone of this thing, and it might be faster to clone up. And by clone, I don't mean like stupid clone, right? So you don't copy like huge amounts of data for nothing, right? I might choose to cleverly give you a copy of that data on the right NUMA node that you're accessing from, right? And this is where things like caching come into place and how you map these things. And when, and again, I did say that make closer function does a lot of magic, right? This is not a function, it's a strategy, right? It's a design. So this is where the challenge comes in, and leveraging how you give out memory to threads. What kind of memory are you using? Are you using some kind of specialized memory allocators? Are you giving out handles through thread local storage? How you're constructing and allowing aliasing to happen in the program, because you can control that through the type system. Where you allow aliasing to happen, where you allow things to move, right? Rust is very eager to move things for you. When do you allow such movement to happen, right? And what does it happen when this move crosses these NUMA boundaries? So this is, and I said this is all the slides, all the Rust code I have, right? So this is where I'm waving my hands a lot, and I'm not showing exact things, but I'm telling you about strategies. And this is where I want to engage you in sort of contesting some of these strategies, because they have drawbacks, right? They're not perfect. Everything is good for some things, not good for everything. Again, cloning things without regard for when you need to do so and what kind of things you're cloning is not a solution, right? So things to think about. how do you want to expose this in service code? How much of these things can you hide in a library? So I work on building a library, right? Building primitives. How much of these things are just library facilities that you don't end up exposing in the programming model? And how many of these things you end up making part of the programming model and exposing as vocabulary types and as instruments so that service builders actually can leverage the same kinds of patterns that the library uses internally. And it's a fine line between ergonomics and efficiency, because if you build something that is highly optimized and efficient, but nobody can understand how it works, and it's very error prone, nobody is going to be successful at using it, right? We see this with any kind of special purpose memory allocator. Like the worst possible thing you can do, aside from using the standard allocator that ships with your toolset, is using a specialized one in the wrong way or on the wrong workload, right? Because you will have worse results. So again, if you're providing programming primitives, or if you're building a programming model that is very difficult to program against, you're not going to be successful in adoption and in actual gains, because people will misuse stuff. So things that can help with this are the type system, things like not send types, core pinning, backup APIs, and so on. Diagnostic tools. So you need more. At some point, the type system is not going to be able to help you. But you can extend this. You can build better errors. You can build custom linters to detect some of these inefficient idioms in accessing memory. You can have runtime detection things that instrument your binary and detect memory accesses, sort of like profilers do. Trace these memory access and identify latency points and things where you get high memory diffusion and where you get unexpected, unpredictable latencies when accessing certain regions of memory. So there's a lot that you can do, but these are not easy things to build. So there's already a bunch of NUMA-aware memory allocators, a bunch of NUMA-aware crates that allow you to sort of query package information and get information about the architecture of the hardware. So there's crates for that, and I was pleased to find that out. And even some specialized data structures that are more amenable for these kinds of memory accesses, right? So this is where I sort of leave this open for discussion, and this is my last slide. And a bunch of these things that I sort of preached as truths, yes, they're backed up by benchmarks. We do, by the way, we're in the process of building these things, right? So we barely started scratching the surface. We do a bunch of research. We base on sort of build on top of other people's research. We do experimentation. We do benchmarks. We build stuff. We invalidate assumptions, and we're very early on in this journey, right? So if you have experiences that are relevant to this, I'm more than happy to chat with you, either here or, I don't know, later over beer. Or you can contact me. I have some contacts here if you, I can even put out an email address if you want. It's not hard. It's my first name, last name at Microsoft. So I'm very happy if any of you have, I would say I'm especially happy if you're having opposing ideas, opposing experiences, things that you feel that are not aligned with what I said. Yeah.
You talked about how to move memory to the proper NUMA part of it. Have you considered to choose CPU bound to NUMA part, which is close to the CPU? I mean,
Yes.
not to move data, but to move the workload.
Yes. to repeat the question, maybe for the recording, have we considered, instead of moving memory when needed closer to computation, moving the computation closer to memory? That's the idea, right? Yeah. Okay. So yes, part of this story is also proper pinning of execution threads and runtimes. I almost avoided going into the runtimes discussion, but choice of async runtime really makes a difference. Things like Tokyo runtime, by default, is a work-stealing thing. So it behaves in an unfriendly way towards new architecture. So if you're using something like a Tokyo runtime, you want something like a current thread model to instantiate a different runtime per each execution core. You want to do some sort of thread pinning to have these execution threads pinned to particular NUMA nodes and their cores, of course, because you end up having multiple cores in a NUMA node, usually. So yes, it's not just moving memory or giving out handles to the right clones in the right region. It's also about scheduling computation in the right place. That is part of the story. And also, I didn't mention part of the story is how you handle I/O subsystems. Also tied into the runtime story is if you're using a readiness-based model or a completion-based model, what kind of system primitives are you using to suck up bytes from the network card? Are you using things like polling? Are you using things like completion ports or IOU ring interfaces to better saturate this read from the network card? So crates like MonoIO and Glumio do a great job of saturating these reads from the network card by using system APIs like IOU ring on Linux. And even on Windows, there's the IO ring buffer API, which is newer, and absolutely by accident looks very similar to IOU ring. So there's going to be sort of easy to copy / implement a similar thing, similar crates for Windows. At the moment, most implementation for IO subsystems on Windows either use an EPOL sort of adapter over completion ports or just use completion ports APIs directly. And there's completely different alternatives in how you might want to read from the network as like server-side loading and event loops to drive more when implementing things like not TCP-like connections. If you're using UDP-like things where you want more throughput out of that for, let's say, media transfers. Also, regarding proper allocation in the right NUMA node, network cards and related to IO subsystem, network cards already do a pretty good job of doing DMA in the right memory region based on where they see the access from. They can generally do this kind of decoding in hardware nowadays to sort of do the right DMA in the right memory when they map bytes from the network card up into the completion buffers. So in general, it's not a bad story. Network cards and drivers are doing a greater job nowadays. Yeah.
I have sort of provocative comment on this. I mean,
love it.
NUMA, especially cache-covered NUMA, is old news. The hardware is moving towards completely disaggregated architectures where shared nothing is not a option, it's the only option.
Yeah.
I mean, Compute Express Link is already a standard. Always there are so many devices out there. There are stuff. So how do you look on this, where you actually need to have programming models for writing code in a completely distributed way, because there is nothing shared.
So this is a step in that direction. So to repeat the question for the recording, there's newer architectures coming our way. It's going to take a while because before they become mainstream, but newer architectures coming our way where isolation is going to be a requirement, and you're no longer be able to cross these boundaries and just incur bigger latency. It's just going to be like not a programming model that you can use. So this is a sort of a step in that direction. It's building a conceptually a single-threaded model where you sort of chop up these things and have deliberate structures where you organize these touch points. Because let's face it, we're not building like theoretical things. We're building real things. And in real things, you will need at some point to share something. Let's say configuration. You're sharing configuration. But even then, you have a choice, like, do we actually make everyone read a central configuration, or do we give each one a copy of that configuration, or at least parts of it, the parts they need, and so on. So there's trade-offs. But you will have, as long as you build a programming model that drastically reduces the programming model of sharing, and encourages a single-threaded model, sort of like the old days single-threaded apartments in COM, if anyone is old enough to remember that. So if you're building a model of sort of single-threaded universe where you have deliberate touch points, then it's going to be easier to do that jump when we get there. We're not there yet. Like the things that you get now in servers, even in big rigs that we buy in data centers, are still your traditional NUM architectures. They're just getting bigger, wider, let's say.
It's really just around the corner.
Let's hope so. So you will end up leaning even more on message passing architectures.
That's the point, I think, because
Yeah.
What we have talked about the whole talk, which was very nice, obviously, was about the locality of
Yeah.
the computing. But if you want to really use your system in a complex way, you just cannot individually program
Exactly.
your single nodes.
Exactly.
You
It's
have to work with
it's in same way as you try to build pure functions without side effects because they're easier to test, easier to reason about, easier to compose. But you cannot build real things with pure functions. At some point you need side effects, at some point you need communication, but you need to be deliberate rather than accidental about how you're designing it. So if you're being deliberate and you're using things that are more amenable to these kinds of architectures like message passing and clever cloning and replication, smart replication, things like copy on read or things of that nature, rather than leaning on traditional synchronization, share everything, screw the heap all over the place, it's going to be easier to do the last step, right? Program in a real distributed fashion.
So my question would be, are there any plans in the Rust ecosystem towards that building that more or less new programming model? Of course, distribution has been here for many years,
Yeah.
but people could have avoided. Now that in the near future, I would say they would not be able to avoid it. So how to put it into the core of the language?
I would say of all the mainstream, I'm not talking about exotic academic things, but from the industrial things, languages, I would say Rust is one of the well-positioned ones in terms of having a stricter type system, stricter aliasing rules. I can see barrow checker being extended even further. So it's, I think, okay, we're not Erlang, but from a practical standpoint, from the industry, practical things, I think with Rust, we're better positioned to get there. It's not there, but we're better positioned, way better than C++, for example. And way better than Haskell, because Haskell is maybe more civilized in the type system, but it's definitely not friendly to program against. So even in Rust today, you have actor-based frameworks, you have a lot of message passing primitives and ideas and crates that you can use as building blocks. So, but it's not like baked in the language at this point. But I could see an addition at some point that could be closer.
Okay, thank you.
Any other things? I'm happy to cut this short on record and just maybe who wants to go goes.
I have like 10 questions, but I don't
Yeah.
want to derail the discussion. So,
Yeah.
is there anyone else with some question? Okay.
Back.
Let's talk about work stealing attempts. Has there been any attempts to just do work stealing but make the scheduler of the task very smart about the NUMA layout and make it like move the tasks to where the data is and avoid the penalty of just minority vision and stuff?
So repeating the question, on the work stealing runtime implementation, have there been attempts to improve the scheduler of the runtime itself to be aware of NUMA architecture and how it schedule tasks on different threads based on where they happen to land on the hardware? Not sure about other experiments out there. We didn't. So writing a good scheduler, writing a good thread pool is not an easy thing in general. Writing one that performs well with these kinds of constraints, it's even harder because it's sort of naively tempting to do something that you think fits the model, but it won't fit every kind of workload and every kind of layout that you might end up having. So we didn't attempt. I'm not saying it can be done. I am saying we didn't attempt. Also, I think the whole idea of thread stealing implies a cost that is an abstraction leak because you end up having send and sync types sort of polluting your types in all layers. It's sort of like it propagates through the things. So even if you're building sort of some boundaries, at some point you end up having to do some kind of synchronization, even if it happens to be inside your own NUMA region. Sure, you isolated it to a NUMA region, but even in that region you have multiple threads, multiple cores, so you need to synchronize, and you pay this synchronization cost. Also, I didn't touch another point on clever allocators, like getting things in the heap in the first place. And I think this is where a lot of research leans into, and a direction we're pursuing is using clever allocation techniques that reduce lock contention over allocating memory, or reduce contention over deallocating memory and collocating memory so that you don't need to synchronize. So we didn't do any research into building a better Tokyo. I'm not saying it should be done. Are we ready to wrap up? I'll take any questions you have, but maybe for the recording if you want to wrap up. Okay. Are we good?
Thank you. Thank you very much for your talk. I think it was very interesting. And
happy to talk more. We'll just stop the recording.
Let's do a round of applause. Yeah.